Hello, my name is Carrie Organtini, and I'm a principal scientist at Waters Corporation. Thank you for joining us today for this session. Today, I will be talking about some of the advances we are making for PFAS analysis. When I talk about the futures of PFAS, what are some of the areas that require continued advancements to keep up with the science? Three of the important topics, and these are topics that I'll be covering today, are sensitivity, chromatography, and contamination control. Let's start first by discussing sensitivity enhancements. And specifically, I am going to be talking about our newest tandem quadrupole mass spectrometer, the Xevo TQ Absolute. What is important in the realm of PFAS analysis with this instrument is the enhanced or improved negative ion performance on the TQ Absolute relative to our old detector technology. And on this slide, we are looking at the ratio of the response of the Absolute to the old detector on the y-axis, and on the x-axis is the product ion mass. And we'll see, and you can see in the circled area that that PFAS fall in kind of a really nice optimal sweet spot for the TQ Absolute when it comes to increased sensitivity. And you can see right on this slide that increase in sensitivity specifically for PFAS. So I've pulled out the 4 EPA PFAS compounds that the EPA has put some health advisory limits around. But this is true across the board for PFAS compounds. And you can see that the TQ Absolute does have a greater response for PFAS compounds than the old detector technology. And as a reference point, on this slide where you're showing 0.01 nanograms per mil or 10 ppt. Increased sensitivity is great, but there has to be a reason for it, right? So what we initially set out to do as far as investigating what are the benefits of having that increased sensitivity for PFAS was to look at a direct inject approach and determine if we could decrease the injection volume on the TQ Absolute to take advantage of that increased sensitivity. And one of the reasons behind wanting to decrease the injection volume is shown on the right-hand part of this slide, and that has to do with peak shape of the early eluting compound. So I'm showing PFBA here. And you can see at the higher injection volumes, around 30 microliters, we start to see a split in that peak. But when we bring the injection volume down to around 10 microliters, we see a nice typical peak. There's also some other benefits to reducing the injection volume, including increasing your column lifetime because we're not injecting as much matrix onto that column, as well as less user interference with the source to do source cleaning, again, because we're reducing the amount of matrix we're introducing to the system. And along with assessing that reduced injection volume that we used on the TQ Absolute, we did a method detection limit study looking at 10 replicates of reagent water spiked with 5 nanograms per liter of a range of PFAS compounds that you can see listed on this slide. And they were taken through the direct inject sample prep and analyzed on the TQ Absolute with 10 microliter injection. And you can see the method detection limits were very low, some below 1 nanogram per liter, ranging up to about 2 nanograms per liter. And there are 3 compounds highlighted in yellow here with higher MDLs, and these are not limits to the sensitivity of the TQ Absolute. These are actually artificially high detection limits because of contamination introduced into this sample from consumable solvents in the laboratory environment. So this is not the high detection limit on these 3 compounds is not due to the absolute sensitivity, but again, because of these are fairly common contaminants in our lab. And then when we translate into actual water samples, I'm showing an example of a wastewater sample here, again, using that direct inject sample prep, which is just a dilution and filtration step. So no real removal matrix is happening here. And in a wastewater sample, which is a wastewater influent sample, so prior to any processing of that sample, we can easily detect PFAS in the sample down to 1.36 nanograms per liter, again, using that 10 microliter injection volume. So knowing that the TQ Absolute was really good for sensitive analysis of PFAS compounds, what else can we apply that to? Because not everyone is doing a direct inject sample preparation. Well, it just so happens around the time that the TQ Absolute was launched, the EPA announced their new health advisories for PFOA, PFOS, PFBS, and GenX. And the PFOA and PFOS interim parts per quadrillion levels sort of shocked the community. So we began to evaluate whether or not these values were they were able to be run on the TQ Absolute. So the values that were, or the health advisory levels that were released by the EPA were in drinking water. And those types of samples require SPE sample preparation according to EPA methods. So we did the sample preparation using SPE and at the appropriate levels for PFOA and PFOS and ran them on the TQ Absolute. So the results of that analysis were that the TQ Absolute is not the limiting factor here. It actually has a really good sensitivity to easily reach the appropriate levels needed for the interim values. What is the struggle is the sample prep part and preventing contamination and introduction of PFAS contaminants during that step. And you'll see here that we were able to, in a normal laboratory environment, to reach appropriate contamination levels that the EPA allows for PFAS analysis. So here what we're looking at is a spike at the interim levels for PFOA and PFOS in blue, compared to the extraction blank in orange, which is a reagent water sample taken through the entire sample prep process that is not spiked at all, and compared to the solvent blank injection, which is shown in green. And that is just an injection blank taken through no sample prep. So we can see that the solvent blank is completely blank for both PFOA and PFOS, indicating that the system itself, the mass spectrometer, the liquid chromatograph system, are PFAS free, or our isolator column is at least doing the job that it needs to do to delay those compounds. We're seeing a little bit of contamination in our extraction blank, but this is below the 1/3 limit that the EPA requires. And then we see a nice response for our extracted PFAS samples. The same is true for PFBS and GenX. GenX didn't struggle at all with contamination, which is really nice to have a compound that behaves nicely. PFBS did have some contamination in the extraction blank, but since the health advisory level for PFBS is so high, this is grossly under spiked for that level, that HAL level. So again, an indication that we can control PFAS contamination to a minimum level in our shared laboratory space and use the sensitivity of the TQ Absolute to reach the levels being required by the EPA. So now we're going to jump from the detection part of the analysis to the chromatography part of the analysis and talk about some chromatographic improvements that we have been making advancements in for PFAS analysis. So a new product line to Waters is the Acuity Premier line, and that is both a LC system itself, so the Acuity Premier is an LC, as well as a brand of columns. So we also have Acuity Premier columns. And what makes the Premier technology is the MaxPeak high performance surfaces. And there's an example here on the slide in the bottom right corner showing what the MaxPeak performance or the MaxPeak surface is about, and really what the surface is great for and was designed for was to prevent non-specific binding to the surfaces that our samples come into contact with along the chromatography system. So we took a look at 70 PFAS compounds and evaluated what that Premier technology did for these compounds. And we looked at that across different concentration levels to see if there was an effect on concentration level at all. So what we found when we looked at all these PFAS was that the compounds that were in the perfluoroalkyl family had a significant benefit to using the Premier column technology. And you can see on this slide why that is. So if we look on the left-hand chromatogram, this is repeat injections of 10 ppb of the perfluoroalkyl injected on the Premier column versus the regular column. And you can see it clearly in on the regular column, those compounds kind of just smear out across the chromatogram. And with that broad of a peak, that really impacts our sensitivity. And it also has implications into data processing. But on the Premier column, we can get an actual real peak chromatograph that enhances our sensitivity as well. On the right-hand side of this slide, we're showing the overlay. Now we're just showing one injection to make it a little more clear. On the top is 1 ppb, on the bottom 0.1 ppb, and it becomes very clear why this you would want to have the better chromatography and higher sensitivity in this case from the chromatography, because at the 0.1 ppb injection level, we've effectively lost this compound to the chromatography, the poor chromatography on the non-Premier column. And finally, the last section I want to touch on is addressing system contamination through investigating alternative isolator columns that also led to some analytical column technology changes as well. So another new product to Waters is the C18AX, or mixed mode anion exchange chromatography column. And if you take a step back and think about how PFAS samples are prepared using weak anion exchange SPE, this column is a very similar concept where we're using, we both have in the column both reverse phase and anion exchange chemistries in that column. So if we use it for sample prep, why not use it as our chromatography, in our chromatography system? And what we looked into was first using this as an isolator column to help delay some of the shorter chain compounds a bit more, and then also as an analytical column for those same types of short chain compounds. And I touched on this a little bit on the previous slide, but the reason why we first looked at this column as an isolator column is that as the use of PFAS has changed from the longer chain compounds being more prominently used to the shorter chain compounds being more prominently used, we're seeing that the reverse phase C18 type isolator columns are not, and analytical columns as well. It's very obvious at the analytical column that the short chain compounds are not very well retained on just reverse phase. So if we're trying to prevent contamination from the mobile phases in the system, the LC system, we can expect that C18 reverse phase column to be sufficient for the short chain compounds, and we've seen that it really isn't anymore. So to investigate this column, I actually purposely contaminated my mobile phases with PFAS standards, and this was probably every PFAS analyst's nightmare, and it was very, very hard for me to do. I went through all of these emotions, but it was worth it, and we're all right. We're doing all right mentally. So before we jump into this new column, let's take a step back and look at what that purposely contaminated mobile phase looked like for PFBA, the C4 carboxylate, and PFPEA, the C5 carboxylate. If we start with C5, the PFPEA compound on the right-hand side of the slide, we can see that there is a delay in the mobile phase contamination on the regular reverse phase C18 column. And how I'm showing that here is the chromatograms on the bottom are a solvent blank. So the only response we're seeing there is the delayed PFAS contamination from the mobile phase. The chromatograms on the top are just a retention time marker using an internal standard for those particular compounds. So this is the retention time we expect these compounds to elute at. If we shift to looking at PFBA, the C4 carboxylate, now, which is a common contaminant in at least my mobile phase and my solvents, if we take a look at what is eluting on the solvent blank, that is now smearing out starting before the peak is actually eluting off the column to a time period after, engulfing that analytical retention time of our compound. And this is going to severely impact the analysis of these PFAS compounds. But if we do nothing else but change that reverse phase C18 only isolator column to the C18AX mixed mode column as an isolator now, it actually provides us 8 minutes of resolution on the contamination front for PFBA from the analytical peak, which is a far cry from what we saw on the previous slide. One of the added benefits that we found for this isolator column, or using this column as an isolator column, was that we can select a larger particle size as well to decrease some of the back pressure that is contributed from putting that additional column on the system. So it gives us a little bit more room in our gradient and what type of gradient we can run by having a lower back pressure. If we overlay the result of the reverse phase only column in orange over the green chromatogram here, which is the C18AX isolator column, I think this really drives home the point of how much better of an isolator column this can be. And here we can really see for PFBA the benefits, again, of using the mixed mode as an isolator column, where we can see now that the sensitivity on the same mass spectrometer, so nothing is changing with the mass spectrometer, but we can gain more sensitivity from using a more appropriate isolator column and removing or delaying more contamination. So you may be asking, what does this mean for the longer chain compounds? So I think it's pretty convincing that it's great for the shorter chain compounds, but also has to work for all the rest of the PFAS, right? So here I'm showing an example of PFOA, and the bottom chromatogram again is the analytical peak retention time that we expect. The middle chromatogram is the original C18 reverse phase only column with about a minute of contamination front delay. And on the top is the C18AX isolator column delay, which is extended to now about 4 minutes. So we don't have as big of a gap that we saw with PFBA, but it's actually better compared to the reverse phase column only. So it does work for all the PFAS compounds. And once we did this work on the isolator column, we started to investigate the use of the C18AX mixed mode as an analytical column as well, because PFBA is kind of on the cusp of not being very well retained on the C18 analytical column we use as well. So that kind of puts out of question anything below the C4 compounds. And we can see here that on a C18 column, the C3 carboxylate, PFPRA, and PFPRS, which is a C3 sulfonate. PFPRA is not retained at all on a reverse phase only column. But if we put in the same dimension C18AX mixed mode column, we now have significant retention of these ultra short chain PFAS, which allows us to now include them into our suite of PFAS compounds. And just by tweaking doing a really quick tweak of the gradient method to elute all of the from C3 to C14 compounds off of this column. Again, this shows that we can both get good retention of the ultra short chain compounds, but also include up through the high chain or long chain PFAS compounds in one single injection. So this is where I'm going to leave you with my story of the futures of PFAS analysis, and I'm just going to leave you here on this slide acknowledging my colleagues at Water that were integral in helping with various portions of this talk. So thank you very much, and have a great day.